This is the next video in the chapter on chemical bonding and molecular geometry. We have learned all about Lewis structures and how atoms are connected to each other with bonds. And now we're going to use that information to predict the three-dimensional structure or geometry of a molecule. So we are going to talk about electron group geometry, molecular geometry, distortions of that geometry, molecules with multiple center atoms, and the dipoles that result. So previously, we talked about Lewis structures. We spent a lot of time drawing Lewis structures correctly for atoms with different numbers of valence electrons, and we use them to predict how atoms in a molecule are connected. They are connected by bonds. They are bonded together. So for example, we drew a Lewis structure for ammonia, NH3, and it looked something like this. We said that it had 3 hydrogens connected and the central nitrogen had a lone pair on it. So now that we know how to do that, we're going to use those because they're not technically an accurate representation of the shape. So we are going to use these structures to predict the three-dimensional structure or 3D structure. We call this 3D structure the geometry, using what's called VSEPR theory. Okay, so we're going to take something like this, which is a Lewis structure, and we are going to use it to predict the geometry or the three-dimensional shape that a molecule will take, which will look something like this. So these are the shapes we're going to be learning how to make. Now, the tool we're going to be using is called VSEPR theory, and that is an acronym. So let's talk about what that means. So VSEPR, or VSEPR technically, is an acronym for valence shell, electron pair, repulsion theory. So it would technically be pronounced VSEPR theory, but that sounds absolutely ridiculous. So we've fudged it a little bit and we call it VSEPR theory. Or you can just call it valence shell theory if you feel better about that. Now, there's a lot of words in this name, but those words are important because they tell us what this theory is about. So let's zoom in a little bit. Valence shell, that's something we've talked a lot about as we learn about electron configurations and where electrons live. So we know that the valence electrons are the ones that are in the outermost shell, the outermost electrons that are used for bonding. So we're going to be talking about those electrons some more. The next chunk is electron pairs. And so we saw when we made the Lewis structures that electrons live in pairs, and they can be in 2 types of pairs, a lone pair that only belongs to 1 atom, or a bonding pair that's shared between 2. So these can be lone pairs or bonding pairs. And it's going to be important that we know which type of pair it is, as you'll see. The last word is repulsion, and that's perhaps the most important of all. This takes us way back to what we talked about at the very beginning when we learned about the structure of the atom, and that was that negatively charged things repel other negatively charged things. So electrons are negatively charged, and so are electron pairs. So negatively charged electron pairs repel each other when they're brought close together. And so to keep that high energy situation from happening, they would prefer to be as spread out as possible. So for example, we have 4 electron pairs over here. We have 3 bonding pairs and 1 lone pair. And those 4 things want to be as spread out in 3-dimensional space as possible, so the negatively charged things don't need to be near to each other. So what we're going to do is we're going to learn how to count these electron groups and give a name to the 3-dimensional geometry that those 4 groups tend to adopt to be as far apart as possible. Let's make a note of our plan. We are going to count the number of electron pairs, but we are going to call them electron groups. And remember, those can be either lone pair electrons or they can be bonding pair electrons. So we're going to count the lone pairs and the bonding pairs surrounding a central atom. And we're going to give a name to each geometry. So we're going to look at what the shapes look like. We're going to name them. We're going to give the size of the angles, and we're just going to get a feel for what those shapes look like. All right, so we are finally going to be drawing some pictures, and I've constructed a few models for you to watch on the video as well. So we're going to be making a table, and that table is going to have 3 columns: electron groups, names, and shapes. It's going to take up about half the page, and we're going to have 5 rows, 2, 3, 4, 5, and 6 electron groups. Okay, so we're going to be counting electron groups, and remember we said electron groups are either lone pairs or bonding pairs. It can't be both, but we are counting both of those types. So our table is going to be a big one. And we are going to be drawing some pictures of molecules. So we are going to use the letter A to stand for the central atom. And we are going to use the letter X to stand for a terminal atom, which is connected to the central atom by a bonding pair of electrons, or a lone pair. So X could represent either of those 2 things. Okay, so we'll start with the most simple. When there are 2 electron groups connected to a central atom, we're going to call it linear. And its shape is going to look like this. So the angle between that bond is going to be 180 degrees. So it is a perfectly flat line. And the molecule is going to look something like this. 180 degrees, totally flat. If you turn it on its side, you can see that it's completely flat. Okay, so far so good. If we have 3 electron groups, it is going to look like this. Those groups are going to be as far away from each other as they possibly can be. Specifically, they are each going to be 120 degrees apart. And there are 3 groups, and they are all in the same plane. This is a flat molecule. So the name for this structure is called trigonal planar. So it's a long name, but it makes sense if you can see where it came from. The molecule looks like this. There's a central atom, there are 3 things attached, and it's perfectly flat. If I put my hand on it, I can touch all of the atoms at the same time. If I were to turn it on its side, you can line all of the atoms up in the same plane. Now we're going to move on to some of the fun ones. So if we have 4 things attached, This one is called tetrahedral because the 4 electron groups could be placed at the 4 corners of a tetrahedron with the central atom in the middle. And to draw this one, we're going to introduce some new drawing conventions to help us represent something that isn't perfectly flat on a flat piece of paper. So the angle between any of these 2 atoms is always 109.5. They don't look like they're the same size angle on the page, but I promise they are in real life. It's just a feature of the way that it's drawn. So let's make a note over here or wherever you have space on your page about these drawing conventions. So when we draw 2 atoms that are connected by a simple line, we're indicating that these are in the same plane. So if you put your hand onto the molecule, you could touch both of these with your flat hand at the same time. But sometimes you can't touch all of the atoms in the molecule at the same time like you can for the trigonal planar. The tetrahedral, that doesn't work. So we have these 2 new symbols. This one is called a wedge, and it's used to indicate that this bond is pointing toward you. So the atom that's at the wide end of the wedge, the X is coming out of the page very, very close to you. That's what that's supposed to represent. So it's called a wedge. And our other one is called a dash, or a dashed line, or dashes. And this indicates that this bond is pointing away from you. So the thing that's at the wide end of the X is going to be very, very far from the camera, from your point of view, and the A is going to be closer. So now knowing what these lines mean, there is a 3-dimensional tetrahedral structure. So if we hold it just like the one in the picture, you can see that both this bond pointing up and this bond pointing to the side are in the same plane. I could touch all 3 of these molecules with my hand at the same time. This bond in the front is coming towards the camera, and this bond in the back is pointing away from the camera. So we use a dash for this one and a wedge for this one in our picture. And this molecule looks like a 3-sided pyramid formed by these 3 molecules with a hat. So the 4 atoms at the bottom form a pyramid with 1 atom on the top. You can also hold it this way, so it looks like there are 2 atoms coming out of the top like ears and 2 atoms coming out of the bottom. Let's move on to 5 electron groups. 5 electron groups, we're starting to get a little dicey, and this is why we have the 3-dimensional models to help us see what these look like. It's difficult to fit 5 atoms around 1 central atom, and you don't see it very often. So it looks like this, and there's several different types of atoms here, and so we need to add a discussion of some of the orientations of where these atoms can be attached to help us have the vocabulary to talk about this a little bit better. So there are 2 types of positions that we can attach these atoms to the center. We can attach them in an axial way, and that means that they form a linear axis or a straight line through the center. So you can probably see the straight line through the center in this picture. It is right here, from the X on the top through the A in the middle to the X on the bottom. That's going to be our axis. So these 2 X's are going to be axial. And the other type of connection is called equatorial. And equatorial atoms form an equator around the central atom. And that equator forms a plane. It's flat. So we can find the plane in this molecule by connecting these three atoms. These three atoms are all in the same plane of each other. So we would call these three x's equatorial. And so if you think of it this way, as this triangular plane in the middle with a point on the top and a point on the bottom, we can see that there's a pyramid formed on the top and a pyramid formed on the bottom underneath the plane. So we call this model trigonal bipyramidal, because the base of the pyramid has 3 points in it for trigonal, and there are or two pyramids formed in the molecule. And there's a couple of different angles in this one. The angle between the axial atoms and the equatorial atoms is always going to be 90-degree angle. And the angle between any two of the equatorial atoms is going to be 120 degrees. So these atoms in the equator are more spaced out from each other. Here is a three-dimensional model of a trigonal bipyramidal structure. You can see the axis running through the center. That's our vertical line. And if we tip it, you can see the equator, the triangular shaped plane connecting these three molecules. So we can spin this model along the axis and watch the equatorial atoms move in a circle. Our final structure is six electron groups attached to one central atom. We are definitely going to need an expanded octet for this guy to be able to share this many electrons with other atoms. So if you took these 6 x's and placed them at the corners of a shape, they would fit in the corner of an octahedron. So this is called octahedral, which is an 8-sided shape that has 6 corners. So if you've played Dungeons and Dragons, you should be very familiar with an octahedron shape. And we can also identify axial and equatorial connections in this shape. If you look closely, you should be able to see 3 axes, 1, 2, and 3, but we only need to mark 1 in our image. So we're going to mark the one in the vertical as the axial. So in the way we've drawn this picture, these 2 red x's are axial, and our equatorial plane in this model is square-shaped, which is formed by connecting these 4 x's into a box. So there are 4 equatorial atoms in this picture. And as in the previous picture, the angle between each axial and equatorial atom is 90 degrees. But because our plane, our equator, is a square this time, the angle between each of the equatorial atoms is also 90 degrees. And our 3-dimensional model for that one looks like this. So you can see the axis running down the center from one atom through the center to another atom. And you can see the plane made up of 4 atoms around the center. So if we spin the molecule around the axis, you can see a square-shaped equator around the middle. So these geometries are called electron group geometries because we have counted all of the types of electron groups. We include lone pairs and bonding pairs in these shapes. And so these are names and angles and shapes you're going to want to practice drawing and commit to memory so you can use them to describe the shape of a particular structure. And in the next video, we'll talk about molecular geometry, which only considers the shape formed by the atoms.